In this video, we'll pick up where we left off deriving the formal trig identities, and we'll start talking about how you can apply that new knowledge. We will look at the angle, sum, and difference identities for sine, cosine, and tangent that I have listed here. And we will also take a look at the double angle identities for sine, cosine, and tangent. And we'll see how these can be applied to both old and new situations. For starters, I do want to just point out here that for copying the identities down, I try to do it in an efficient way. So if you look here at the sum and difference identities, I write cosine of alpha plus or minus beta, and then later in the identity, see minus or plus. So that's the way I can tell you cosine sum and difference identity all in one line. So it's written second as minus or plus because cosine sum identity has a minus and cosine's difference identity has a plus. And then you can see, for example, how it works for sine and how it works for tangent. Okay, so let's put these to work. In our first example, we're going to apply what we learned with these new identities to the unit circle. And the unit circle was the first thing we learned in trig, so we're going way back here. So you'll recall deriving different ordered pairs on the unit circle, like 1, 0 for an angle of 0 degrees, and of course up here 0, 1 for an angle of 90 degrees. And if you remember, we did a little bit of geometry to derive the coordinates at 45 degrees, root 2 over 2, root 2 over 2, and then the coordinates at 30 and 60 degrees, which are root 3 over 2, 1/2, and 1/2 root 3 over 2, respectively. What we're able to do now is think about the unit circle chopped up into even 15-degree increments. So we kind of complete the unit circle in a sense. So when we think about the x and y coordinate at 15 degrees, of course, those will be cosine of 15 and sine of 15. And then the x and y coordinates at 75 degrees, of course, those would be cosine 75 and sine of 75. Okay, but we can actually figure out the exact value for cosine 15, sine 15, cosine 75, and sine of 75 using the angle, sum, and difference formulas. So just as a quick example of how that might work is if you wanted to know what cosine of 15 degrees was exactly, you could think of it as cosine of 45 degrees minus 30 degrees. Okay, that's a difference of two known angles, and we can then use the cosine difference identity, cosine of the first times cosine of the second, minus plus sine of the first, sine of the second, and you can just work out each of those individual sine and cosine problems to establish that this will be equal to root 6 plus root 2 over 2 times 2, or 4. And that right there is the exact value of cosine of 15 degrees. If I wanted to know the exact value of, say, sine of 15 degrees, I could use a difference identity as well. Same difference, 45 degrees minus 30. And sine's identity would tell me to do sine of the first times cosine of the second plus cosine of the first times sine of the second. And that, of course, would be equal to root 2 over 2 times root 3 over 2. You can see I often make this mistake here where sine's difference has a minus sign and cosine's difference has a plus sign. Minus root 2 over 2 times 1/2. And that would simplify to root 6 minus root 2 over 4. That's the y coordinate right here. Meanwhile, if I wanted to go back here and work out cosine of 75 degrees and sine of 75 degrees, I could use the angle sum formulas instead of the angle difference formulas, or I could just think about it through the lens of a cofunction identity. I know that sine of 15 degrees is the same as cosine of 75 degrees. I know that cosine of 15 is the same as sine of 75. So I've actually already worked out the x and the y coordinate at that particular point. In addition, if you wanted to complete the entire unit circle, you could just continue to use the symmetry the way we normally would, where if you had to jump from one quadrant to another, just pay attention to the reference angle in the first quadrant and whether the x or the y would be positive or negative in that quadrant. Okay, so that's kind of going way back. Let's think now about how we could apply what we've just learned with these new identities to maybe some old properties. So these are some true or false questions. We before talked about some of these properties via symmetries on the unit circle, but now I can think about them a little bit differently. And if I'm ever maybe a bit confused about a symmetric relationship with sine or cosine, I could use the new knowledge that I came up with to check it. So what that might look like, for example, is in letter A, if you wanted to know whether sine of 2 pi minus theta was equal to sine of theta, you could apply the sine difference identity, which would be sine of the first angle times cosine of the second minus cosine of the first angle times sine of the second. And you could simplify it and see if it's equal to sine of theta. Well, in this case, you'll see that it won't be, because sine of 2 pi is equal to 0. So 0 times cosine of theta minus, and cosine of 2 pi is equal to 1, so that's 1 times sine of theta. So that would not simplify to positive sign, but it would simplify to negative sign, so I could then conclude that that statement was false. Meanwhile, the second statement here, if I wanted to know if sine of theta plus 45 degrees was equal to cosine of theta minus 45, again, I could think about this by rotating on the unit circle, but I guess instead I could say sine sum would give me sine of the first times cosine of the second plus cosine of the first times sine of the second. That's the left-hand side. And I want to know, is that equal to the right-hand side? I'll apply cosine's difference identity here. So it would be cosine of the first times sine of the second plus sine, nope, I got the wrong identity here. As you can see, they're easy to mix up. It's good to do these with a list right in front of you. Cosine's difference identity would be cosine of the first times cosine of the second plus sine of the first times sine of the second. So I want to know, are these in fact equal? Well, at the moment they don't look exactly equal, but when you work out cosine of 45 degrees, you'll get root 2 over 2. And likewise, when you work out sine of 45 degrees, so the left-hand side simplifies to that. And on the right-hand side, you'll see that, oh yeah, we're going to end up getting the same thing. So this was a statement that was actually true. Yeah, there's a lot of different ways we could think about the truth value of this statement. You could think about it graphically. You could think about it through rotations on the unit circle. But now we have yet another way to look at it, just by quickly applying an identity. Okay, how about maybe where can we really push our thinking forward a little bit? In example 3, here is a trig equation that we would not have been able to solve before. It says find the solutions on the interval from 0 to 2 pi, where sine of 2 theta is equal to 2 sine of theta. In fact, this may have been a mistake that a lot of us made in the beginning before we talked about like graphing and all of that. This is a sine that has a frequency of 2, meaning it does 2 cycles in the standard 2 pi radians, and on the right hand side this is a sine curve that has an amplitude of 2. So we want to know, we know that these are not always equal for all values of theta, but they're possibly equal for some values of theta, and we want to be able to solve it. So what can we do here? Really, the only thing that you can do is you can say, oh, I have an identity for sine of 2 theta. I can substitute that identity in for it. And sine of 2 theta, according to that double angle identity, when I use that double angle identity, I get 2 sine theta times cosine theta. So I have 2 sine theta, cosine theta is equal to 2 sine theta. This is the equation that I wish to solve. Remember that we don't want to divide both sides by sine because sine equals 0 frequently. So instead you want to group everything on the left-hand side, like so, and factor out a common factor. So in this case, the common factor is sine. So it's 2 sine theta times cosine theta minus 1 equals 0. And that tells me then that either 2 sine theta equals 0 or cosine theta is equal to 1. And this is going to generate some solutions for me. So if I picture my unit circle, maybe I want to know where sine is equal to 0. So sine is equal to 0 right there, that horizontal line through y equals 0. And I want to know where cosine is equal to 1, and cosine would be equal to 1 right here. Okay, so I can see that the solutions that I'm getting are at theta equals 0 and theta equals pi. And then 2 pi, of course, but that's not included in the directions. So there we go. Those are two values where the sinusoid sine 2 theta crosses the sinusoid 2 sine theta. And we wouldn't have been able to solve that without our double angle identity. You'll see a lot of different trig equations that the identities are really, really necessary. And then here's a fourth example. One other thing that we might be able to do is extend our knowledge by proving more difficult trig identities. So this one would be show that this is true for all values of theta. So I'll start on the left-hand side. So when I start on the left-hand side here, I have 4 sine theta times cosine theta. That looks kind of familiar. And it's multiplied by 1 minus 2 sine squared theta. That also looks kind of familiar. So, okay, let me see. What we're doing here is we're seeing how these might relate to some of our new identities. So I'll just scroll back up here real quick. And where have we seen these kind of things before? So I don't see a 4 sine theta, but I don't see a 4 sine cosine, but I do see a 2 sine cosine. And right above it, I see a 1 minus 2 sine squared theta here. This is what I mean when I say it's good to have a list of these identities in front of you when you're doing problems, because sometimes they pop up and you have to sort of recognize what they are. Okay, so what I'm going to do is I'm going to substitute out 1 minus 2 sine squared for cosine's double angle, and I'm going to see if I can do a little rewriting in order to use sine's double angle as well. So that's going to look like this. So this expression is equal to 2 times 2 sine theta cosine theta. 2 times 2 is 4. And times 1 minus 2 sine squared theta. So that's going to be equal to 2 times sine's double angle identity. I'm just pointing out here that 2 sine cosine is sine's double angle identity and replacing it with sine of 2 theta. And then I'm going to multiply by cosine of 2 theta because right here I noticed cosine's double angle identity. Okay, I'm actually really, really close right now. What I'm at now is structurally something that once again looks like sine's double angle identity. I see here 2 times sine of an angle times cosine of an angle. And that structure is what sine's double angle identity is. So what I'll do is I'll rewrite this as sine of twice the angle. Now the angle in this case was 2 theta. So that is sine of 2 times 2 theta, and that's sine of 4 theta. And that's it. So this video hopefully gives you an idea of some of the things that you can do with the new knowledge that you acquired and all of those derivations that we did in the last 3 videos. All right, thanks.